an exponential function can be modeled by, and so let me give you the equation that we can use for exponential functions. And so you're jotting this down here. Let me move this up here a little bit. It's there. And so here's the equation. So let's go with green here. And we have y equals a times b to the power of x. And this is the equation that we're going to be using for this tutorial. And let me tell you what a and b are. With a, the initial value, and with b, the growth/decay factor. So that's what a and b are. Okay, so b decides if something is growth or decay, and then a is the initial value. So why don't I give you guys sort of a quick chart? Like, let me show you a way that you guys can make graphs of exponential functions like so quickly. So let me draw this for us here, and let's do this in purple. So why don't you guys draw something like this? Make a chart that says like this. So let's go a greater than 0, and then a less than 0. And up here, we'll go b greater than 1, and then we'll go b between 0 and 1. And then why don't we break this off into some sections where it goes like this here, it goes like this here, it goes like that there, and it goes like this, and it goes like this. And so let me draw the x and y axis. Like that there, like this here. Try that again. Okay, so here's what I'm saying. If I give you an equation, you can compare the values of a and b, and depending on what a and b are, you're going to have the following graphs. There are 4 cases, and here's what they look like. So here's one of them, like that there. Here's another one, like this here. Here's another one, like this here. And then the 4th and final case looks like this. So jot all that down while I get an example going here. So for example, down here it says example. Sketch the graph of. And let's do a couple of examples here. And what we can do is we can do these, but without desmos, without a table of values. We can just use our chart. So for example A, what if you have this equation? Let's go with 1/2, and let's go with 4 to the power of x. And what I should also do here on this chart is I should put some summaries, some labels. This is going to be positive growth. This is going to be positive growth here. Let me change the format to a smaller font. Let me leave that there. So this is going to be positive growth here. And the one to the right of it is going to be negative growth. So let me actually just go like this here. This is positive growth, and this is positive decay. Let me leave that there. And then down here, if I use the text tool, this is going to be negative growth. And the one beside it is going to be negative decay. All right. So these are the labels, folks. This is how you can classify a given equation. So for our example down here, because b is 4, right? That's the value of b. B is 4. 4 is greater than 1. And then this 1/2 is positive. So because the 4 is greater than 1, that means that this is growth. And because this is positive, that means that this is an equation that is an example of positive growth. So if I wanted a picture of this like in 2 seconds, I would look at my chart for positive growth, and that tells me that my picture would look something like that. You see what I'm saying? So the purpose of this chart is to be able to give you a really rough idea of what an equation looks like. It would look something like this here. Let's try another one. So let me get my eraser tool. And let me erase the equation. And let me give you guys a different one. And then we can do something else here because there's a lot to get through. So what if this time, for example, B, we said y equals -2, let's go with 1/8 to the power of x. Okay. So decide on the classification. You see this number, that's 1/8. 1/8 is between 0 and 1. So it's going to be decay. And because this number is negative, this is going to be negative decay. So what would the graph of this look like? Like a really rough sketch here on our papers. Well, what does negative decay look like? Based on our chart, negative decay looks something like this. Something like that. Okay. And what I also want to throw at you, making connections to the next concept before we get there, what I also want to throw at you is that this graph here, this graph down there, it has a horizontal asymptote. I'll draw it for you in green. You see that horizontal asymptote? That horizontal asymptote is at 0. And the reason that it's at 0 is because this equation had a +0 at the end. You see this number in the back? All your equations for exponentials, they're going to have a number in the back. And that number in the back, that's going to be HA, the horizontal asymptote. These guys will always have a number in the back. And whatever that is, that's going to be your horizontal asymptote. And then whether it's positive or negative growth or decay, that'll decide the shape. So let's do one more actually. Let me wipe all this off the screen here. And let's do another one here where we can have an asymptote. And then you guys can sort of see how to graph this quickly. So how about we go one like this here? Let's go back with purple. So example C. How about -2? Let's go 5 to the x. And how about +4? So here's what we're saying. Here's the x and y axis. Let's pretend that that's 4. So because you have a number in the back of your equation, that constant, that's going to be always the horizontal asymptote. So you know that this guy here, that's the horizontal asymptote, which means you go to 4 on the y-axis and you make a dotted line. Something like that. And then decide what the graph will look like. Well, this 5 is b, right? This is the value of b in the parentheses, and b is greater than 1. So you know that this is going to be growth, and that this number is negative, so it's going to be negative growth. So this is an example of negative growth with a horizontal asymptote at 4. So negative growth looks like this here. And so we need negative growth, but it has to respect the asymptote. So I want this general shape here, negative growth, but it has to take place, or it has to respect this asymptote. So it looks like this. It would look something like that. And if ever you're unsure, you could always go to decimals and type in the equation. I'm okay with that. You know that I'm okay with that. But it's nice to know how to graph things without decimals by relying on some sort of a technique, in this case, this chart. Another thing that I want to throw at you before we move on to the last part of this tutorial is how would you find the domain and the range, and maybe let's say the Y-intercept. So let me open up a text tool here. So let's go domain. Let's go range, and let's go Y-intercept. And let's make this text a little bit bigger. There we go, much better. So you guys can copy this down here. Forgive my voice, it's been a long day of teaching. My voice is a bit hoarse. So let's see here. So for the domain has to do with the x values. And if you remember the picture that I was on the board just a moment ago, let's see if I can just quickly sketch it. That was at 4. And then we had this asymptote here. And the graph itself looks something like this here. Okay, so looking at our graph, this graph goes to the left and it goes to the right forever. It goes left and right forever, which is why the domain is going to be all real numbers. We've seen that in the past. That's the domain. And as a matter of fact, the domain for all exponential functions is going to be all real numbers without exception. So for all exponentials, the domain is all real numbers, period. The range has to do with the y coordinates. we're looking at this graph here. What do all of these y coordinates have in common? Well, the one thing that they all have in common is that all of these y coordinates on this graph are below the asymptote at 4. So for that reason, we can say that the range is y less than 4. Isn't that right? Because all of these y coordinates of all of these points have a y coordinate that is smaller than 4, which is why that's the range for that one. And so the last thing to consider now is the y-intercept. So looking at our graph here, the y-intercept, if I use a little pen here, that's the y-intercept. And notice that for the y-intercept, the x coordinate is going to be 0. The y coordinate is what you have to find. I think in the homework and in your midterm, they're really interested in like the domain, the range, and like the y-intercept. So how would I find the y-intercept? I plug 0 in for x. So go to your original equation, but instead of x, you plug in a 0. So let's see. Instead of x there, let's plug in a 0. I'll just leave it there actually. So let's plug in a 0. So this would be -2, 5 to the 0 plus 4. 5 to the power of 0 is 1. 1 times -2 is -2. And the -2 plus 4 is 2, which is why this y-intercept is, 2. It keeps erasing like the whole thing. Let me just put a 2 here. I'll do it like in purple. And so this would be 2, right? That would be 2 right there. And that makes sense because look, it's above the x-axis, so it has a positive y-intercept. So that has to do with like graphs and equations and stuff and investigating a function like the domain, the range, and the y-intercept. So the last part for this video, we can look at equations. So here, why don't we try a couple of equations? So the directions are to solve each equation. And let's do a few of them. And then that should be good for the homework, right? Little video summary here. So how about with this equation here? We want to solve each of these equations. So example A, how about we go 5 to the power of q? Let's go equals, let's say 5 to the power of 6q minus 8. I want to solve this equation for q. Completely just made this up. I have no idea what the answers are. But let's see. Notice that this is 5 and this is 5. So can we all agree that because the 5 is equal to the 5, wouldn't it be a logical conclusion that q would therefore have to equal this? Wouldn't it be a logical conclusion to say that because the bases match, that the exponents would also have to match? Couldn't we say that q equals 6q minus 8? I think that would be a logical conclusion. After all, the 5 and the 5 match, and so this exponent has to equal this exponent. So I think that that would be a logical conclusion. And so let's solve for q. I'll put an invisible 1 there in orange because there's a 1 right there. These are gone. And so we have -5q equals -8 divided by -5. And so the double negative becomes positive. And this is the value of q. Right, so solving exponential equations. So we did the graphs, we did the equations, we did the investigations, we defined an exponential, we looked at the chart, like the summary. Now we're doing a couple of equations to finish off this tutorial. What about another equation that's a little more interesting? What about an equation that looks like this? For example, B. Let's go with, let's go with 6 to the power of w plus 4 equals, let's say, 2 to the power of 16. You see, right away, I do not have the convenience of the previous problem because in the previous problem, the bases were identical. Here, not so. This says 6 and this says 216. However, we can get creative. You see, instead of 216, we can write down something that 216 is known to equal. 216 is the same as 6 to the power of 3. Now, what was the whole point of even doing this? Because now the 6 matches with the 6. And so we can say that this exponent has to equal that exponent, right? You set the exponents equal to each other. once you have a common base. Okay, there it is there. All right. And let's try one more and then we can dismiss here. So let me wipe this clean. So again, what this video that you're watching is just a tutorial based on yesterday's lesson. Right now, we're not actually zooming with a class. This is just a tutorial that I'm creating on my own. And what about something like this here for the last one for today? Let's go with, how about 25 to the power of 3a minus 7 equals 1 over 5 to the power of, let's say, a, let's go minus 5. Again, completely made this up. I have no idea what the solution is. But I do know what my strategy is. My strategy is to get a common base. I see a 25 and I see a 1/5. So my brain is thinking of the number 5. You see, in here, it's supposed to say 25. But instead of 25, what if I write 5 to the power of 2? That's being honest. That's still 25. And on this side, instead of writing 1/5, do remember here as a side comment, as a quick FYI, remember that 1 over 5, is the same as 5 to the negative 1. It's one of our properties from algebra. So that being the case, I'm going to write 1/5 as 5 to the negative 1. I'm definitely going to do that. Another FYI that I want to throw at you that's relevant is this one. A to the power, if you have a to the power of b to the power of c, like if you have an exponent to the power of an exponent, this would be the same as a to the power of b times c. You'd have to multiply b and c to get this here. So with that knowledge in mind, here's what we can get. Why don't we distribute the 2, and why don't you distribute the negative 1? And that'll give us 5 to the power of 6a minus 14 equals 5 to the power of negative a plus 5. And what was the whole point of doing all of that? To get the common bases. You see that? The bases are the same. And so we can go, this exponent equals this exponent, 6a minus 14 equals negative a plus 5. And it can be shown that a would have a value of, it looks like that's going to be 19 above 7. 19 over 7. Final answer. So if you have any questions, let me know. I do hope that was helpful. Give the homework a go now. And again, let me know if you have any questions.